So we're here, the SID Display Week 2019, and who are you?
My name's Roger Barker. I'm a product marketing director for ARM Limited.
And right here at this show, you're launching the Mali-D77.
That's right, Mali-D77. It's our new display processor that we're aiming specifically at the head-mounted device market. It's got some extra special secret sauce in there to deliver asynchronous time warp, chromatic aberration correction, lens distortion correction, all in hardware in real time to deliver a smoother experience using far less power and delivering a better experience for users in time.
So these are some of the things that it works to fix. So asynchronous time warp, lens distortion.
Correction, chromatic aberration correction. We're able to compose multiple layers, up to 4 VR layers at one time. I have to move out the way.
Yeah, and so all these have never been done before in this kind of way that you're doing it?
That's correct. In the past, this has all been done on the GPU. GPU needs lots of horsepower to actually carry this out at high resolution at high frame rate, and high horsepower means it's high cost because it uses a lot of power, uses a lot of energy, and it needs very expensive GPUs to handle that at a high performance level.
So this stuff, those algorithms have existed before, but they were just done on the GPU. They've not had a dedicated IP to kind of accelerate this?
That's correct. So that people have they all have their different variants on the algorithms, but we've developed an algorithm that can run in hardware, and we can do that in a single pass through the display processor, which enables a far better experience.
And so that means it's going to be part of the Mali IP, or it's like one of the part of the GPU?
It's a part of the Mali display processor. So the Mali display processor should be used alongside something like the Mali GPU. Alongside video, alongside CPU, so we have a whole multimedia suite, so we can provide all the components, or for people who don't use our products, they could still use our display processor.
So ARM is like really good at getting lots of different IPs in there, right? And the
Yep.
SoC, there's all these different things going on. There's and it's been a while that ARM has been doing the display part too.
We've been doing this for about 6 years now. We bought a company called Evertronics, who are based in Poland, in 2013, and we've gone through about 4 iterations of products now, and we're now onto a new architecture which we introduced 2 years ago, which we call Comida, and the D77 is built on top of the Comida architecture.
Is it also related with the Apical acquisition?
It works with the Apical IP called Assertive Display. So at this stage, we still have separate IP for Assertive Display and for the display processor, but they're optimized to work well together. So when we designed Comida architecture, we'd already acquired Apical, and we were making sure all the interfaces, both hardware and software, was as smooth as possible to give a better experience. AR and VR has been a buzzword for a few years now, Yep.
but is ramping up for the next level. You want to have, for it to be really, really successful, it needs to be huge resolutions,
Yep.
huge functionalities, and this is really important for this.
So this is what we're seeing, is that the initial experiences people have had with VR haven't been as good as they'd like, and this has partly been because the processors weren't able to process enough bits at fast enough frame rates to enable a smooth experience. And we've identified specific areas that we thought we can improve in the display processor to offload the GPU, to allow it to spend more of its time, give it more horsepower to actually improve its delivery of the experience, goes to the display processor, and then that manages that all the way through to the display.
So when you talk about 15% overhead on the GPU performance, is that the stuff you're doing in this IP?
Yes. So as well as the 15% performance uplift, or performance freedom, I guess, if you like, we're freeing the GPU to focus on what it should be doing. The other key thing here is, because we've freed it up from doing that, it isn't forever or constantly being interrupted and having to switch context between developing the game, creating and rendering what it needs to for the game, and then supporting the head-mounted display. And that's the key part of this. We're stopping it being interrupted, so you can guarantee the flow or improve the guarantee of the flow through the GPU, and then through the display we can guarantee that we can hit the frame rate of the target display.
And you have some other stuff you're talking about. You just did a long presentation, and some. What's the Timewarp about?
So Timewarp, it's a method of reprojection to mitigate the display type pipeline latency. So this is the problem that has happened in GPUs, where the GPU hasn't been able to render the next frame fast enough for when it's due to be presented to the processor, to the display. Sorry. So basically, what Timewarp does is you take account of head movements, and you can reproject based on those head movements the same frame
In real time.
in real time. So basically, this prevents the jerky effects of missing the frame that's created by the GPU.
So when you move your head, instead of being jerky, it's going to move inside the image.
Yeah.
In the direction you're moving your head. Before
The
you get
the image will
real...
move much more smoothly. There won't be the jerkiness. It will be much closer to the actual head movement that you're making. So there are links between the sensors on either in the phone that's in the head-mounted display or on the head-mounted display device itself, where the gyroscopes and other things are allowing you to work out the head pose, and that's being fed into the display processor. So the display processor takes care of that. The GPU doesn't have to get involved. The GPU just continues functioning on delivering the game as good performance as possible.
Nice. And you're talking about something else here?
So pre-distortion we're talking about. So typically when you're using a head-mounted device, you have some bottle-top lenses between you and the display to give you an improved field of view, or an apparent improved field of view. And if we go on to the next couple of slides, we talk about this a little bit. So if you have the rendered frame, so the top left frame there is the frame that the GPU is presenting, so it's nice and crisp, it's exactly what you want it to be. If it's fed through a lens, you'll then get an effect called pincushion distortion, and you can see that it's squeezed in from all the sides, and it has a negative impact. So to compensate for that, what we do is do the inverse distortion. We create, bottom left there, we create a barrel distortion, which offsets the pincushion distortion. And so when it goes through the lens, you get a good rectilinear image, which is what you want and which the GPU originally produced.
So do you have to calibrate this to every different headset?
Yes.
Every different lens?
Yes, you will have to.
Maybe the user could do that, or the manufacturer would do that?
You'd expect the manufacturer to do most of that, but most devices now have levers and things so that you can optimize it for yourselves. You can change into pupillary distances, things like this. So part of what we have to do is ensure that within the firmware that we provide, this can be upgraded, not upgraded, this can be adjusted by the user. And this is something that the OEM will have to do in their software as well. They'll create software which will enable the user to calibrate it for their own use, for their own comfort.
And you have some more things you're adjusting?
Yeah. So one of the things on this one, the top left frame was the one rendered by the GPU. The bottom right frame is after it's gone through the distortion correction. But as you can see, it's not clear. It's still a bit fuzzy. And the reason it's a bit fuzzy is because of chromatic aberration. So as the different color channels pass through the lens, they have different refractive indices, and so they refract differently. So what we have to do is we take the same approach that we took with the distortion, and we do the inverse of this before we pass it through the lens, and that means we get to a stage where we have a nice sharp image, which was the image that was comparable to the image that was originally produced by the GPU.
It's because in science, what's called every color has a different
channel.
What do you call it? Channel.
Color channel. Yes,
It
so
has
a wavelength. So they're different
right?
wavelengths. Yes.
So that's what create chromatic aberration in every lens.
That's right.
Every lens has this issue?
Every lens will have that, and
it has to be
you always
fixed by
have
software.
to offset that. Today it tends to be fixed in software, and what we're doing, clearly we're doing it in hardware, so we're alleviating the GPU from having to do it to make sure the GPU can focus on what it does best, and we can reduce the power requirements and increase the performance of the end device.
Nice. So you here the SID Display Week to talk about all this, because
Yep.
this is the mecca of the display industry.
That's right.
And all the AR, VR display makers are right here.
That's right.
And they all have to think about your solution and when they create the next gen devices.
Exactly. What we want them to do is make them aware of what we're doing. We also want to be very aware of what they're doing and what their future developments are. So as we move forwards, we can get to a position where we're able to cope with whatever they are bringing out as well. So that's the key activity for now.
I'm guessing maybe you have access to some of these totally amazing future AR, VR displays. The dream is people need to, like last year or 2 years ago, Google talking about they want to have huge amount of, like 18K displays.
Yep.
And with foveated and with eye
Foveated
tracking,
rendering, eye tracking, all sorts of
everything.
clever things like this. Yes.
And it's all more or less related also, right?
They're related. The VR and the AR are different from the display perspective, and the requirements are different, but they are related. And the things that we're talking about here will be important in AR as well. And clearly we're talking to many different people to understand what will be required in the future, what is being required in the future, and we're helping to influence that so that we can make sure that we are able to address it when the time comes for it to be available. We're still a little way away from this in AR in particular, but it's something what ARM will be working on through over the next few years.
What's the other challenges for AR that's not in here?
If you think about it, it's related to light. It's looking at transparent lenses. What do you actually really want to see on those lenses as well? Are you just looking for information? Are you looking for full video on there? Are you wanting them to be adaptive? Can you use a headset that doesn't look like a baseball helmet? Baseball helmet? Wrong one.
Yeah.
American football helmet.
Yeah. So how about is it possible to have this dream where you have somebody sitting over there in AR exactly
Yes.
on the chair?
Yes.
And that's part of this too?
Yes, that's where we want to get to. We're a fair way away from that being a common reality, but that's where we want to get to.
All right. So thanks a lot for doing all these technologies that the whole world could potentially embrace.
That's the aim. We just want to make it easy for people to use. So